So when you see one of these, remember, this is the dust of the ancient stars. And the dust of the ancient stars we call elements and arrange them in the periodic table of the elements. So how do we know anything about the sun and its chemistry and the stars and the chemistry? Well, it's the rainbows. It's the rainbows that tell us secrets about the suns and the stars. It's the rainbows that tell us just about all the secrets of the sun and the stars. So rainbows are like billions of little prisms. Those prisms are water droplets. And for those of you who know physics, this is an interesting thing. We see the white light coming in, and it's being bent, but the visible light is electromagnetic waves that have different frequencies, and the different lights are bent in different ways based on their frequencies. Well, let's talk about something that they teach in chemistry class, flame calorimetry. Calor has to do with heat and thermodynamics and measuring that. If we set something on fire, it gives off a flame of light. And if we put that light through a prism, it will form a very specific spectrum of light. And everything that burns gives off a specific signature, and we can measure that. We can measure that here on Earth, and we can point the telescopes out in the sky and see the same signatures coming from the stars. So anything that burns is going to have a unique spectrum of light that can be measured. The sun and the stars burn with specific frequency of light that tell us the chemistry inside of them. And so for those of you who remember the old vinyl LPs with the little grooves of them, saw a guy who could look at the grooves of a record and tell you, he was on David Letterman, could tell you what was on the record because he could see the patterns in the grooves. And we can do the same thing with the spectrum of light. If we divide the light into its various spectrums, there will be a signature just like grooves on a record. So it's with very special glasses that we can see the entire spectrum of electromagnetic waves. So light is an electromagnetic wave, and the spectrum that we can see is very, very tiny. This is the entire spectrum of electromagnetic waves. When you hear about gamma waves, when you hear about X-rays, when you hear about ultraviolet, when you hear about infrared, microwave, AM, FM radio waves, and long radio waves, well, they're just like light that you can't see. Don't believe me? Go home and take your cell phone or take any digital camera and take your remote control, which has an infrared LED on the front of it, and when you look at it, it doesn't light up at all. But when you look at it through a camera, you will see it light up because your camera can see frequencies that you can't. And our telescopes work the same way. Try it. It works, I promise, unless your remote's not working. So anyway, we see a very tiny spectrum of the entire electromagnetic waves. However, we can use instruments and point them at the sky and see the entire spectrum of electromagnetic waves. Well, I listened to somebody giving a sermon who uses a cell phone to tell me that that's all that business about physics is completely ridiculous, and I can assure you all the physics that makes your cell phone work is all the same physics that they use to point the telescopes in the sky. So when the first cell phones were being developed in the 50s, well, the scientists had a problem. There was some buzzing background microwave. Everywhere they pointed the antenna, there was some bzzz coming in at some frequency. And they didn't know what it was. Maybe it's pigeon poop, maybe it's a broken resistor. It took them years and years and years of meticulously cleaning and redesigning to try to make this buzzing noise go away. Well, some physicists on the other side of the planet knew what that buzzing noise was, but they had no proof of it. And so to understand those microwaves coming from space, you have to know something about the Doppler effect. You know the Doppler effect. The Doppler effect, you hear it on TV like a bullet, or a race car. Now, if you're in the race car doesn't go, if you're in the race car, it goes, right? Pretty close, all right? But if you're sitting and watching the race car, it goes, all right, so when it's coming towards you, the pitch of the sound is high, and when the race car moves away from you, the pitch drops. And if you'll notice that when cars go by, when an ambulance goes by, when something's coming towards you, woo, 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 and as it goes away, woo, woo, woo. And so that's the Doppler effect. Now, sound is not an electromagnetic wave. Sound is a physical wave, just like waves in the water, but still, electromagnetic waves and physical waves, all waves behave with the Doppler effect. Whatever direction it's going, the wavelengths are tighter together. The higher pitched sound is in front of the race car. The lower pitched sounds are behind the race car. Well, electromagnetic waves behave this way, and we learned in the early 20s that when we point the telescopes into the stars, we can notice this Doppler effect. And we know this from something called the hydrogen shift. So to make a star work, we have to take hydrogen and fuse it into helium, and this reaction causes a very specific frequency of light. We can see it in our sun, and we can point the telescopes at the stars and see the same thing happening. However, when the stars that we see, when we point the telescopes out, we see the stars moving away, and we can tell they're moving away because that frequency of light that happens when the hydrogen is being fused into helium changes its frequency. And so we call that the red shift, the hydrogen shift, and it's the Doppler effect. So this is the frequency of hydrogen burning in our sun. This is what the signature of hydrogen fusion looks like on our sun. And for those of you who can see this, we can see that the patterns are nearly exactly the same, but they've been shifted in the red direction. This is because of the Doppler effect. And so we know this between the Doppler effect and developing your cell phones, which work pretty well. This background microwave radiation that the first cell phone developers were trying to get rid of, they couldn't get rid of it because it is a microwave coming from every direction of outer space. And this microwave coming from every direction of outer space is a very bright light from a very big bang, and that light has been stretched and stretched and stretched because of the Doppler effect. So astronomy is something very fascinating to me, something very important to the University of Hawaii. I can assure you there is a reason that the top of the mountain is a sacred place and a great place to look at the stars. The mountain whispers the wonders of creation. The mountain whispers all sorts of things. And the first person to ever say that to me was a guy named Anthony Natividad. Does anybody know who this? He played the nose flute, and he passed away about a year ago, which was very sad. I met him on jury duty, and I thought they had hired him to be the entertainment, but he was just sitting around being the entertainer. And he'd play the nose flute in either ear and try to tell the story without crying. When he played, he would say, "If you stare at the mountain, it will whisper to you." And so that's a secret that he told me, and something I found to be true, which corresponds with all this business that everyone likes to fight about.